We've seen that strain and stress are symmetric matrices. In 2D, they're 2 by 2 symmetric matrices. Strain consists of the components epsilon xx, which is du hat by dx, epsilon xy, which is 1/2 of du hat x by dy plus du hat y by dx, epsilon yy du hat y by dy, and sigma has the 4 components. Sometimes, particularly for computer implementation, instead of keeping strain and stress as 2 by 2 matrices, it's helpful to write them as vectors, like this. So epsilon can be written as a vector with the 3 components, epsilon xx, epsilon yy, and gamma xy, if you note. And that can be written as this matrix of derivative operators times u hat x, u hat y, and we call this matrix B. And similarly, sigma has 3 components. So notice that the third component we called gamma xy, which is actually twice epsilon xy. So why is gamma xy defined as twice epsilon xy? The answer is because if we do the dot product of the 2 by 2 matrix versions of strain and stress, we want to get the same answer as if we did the dot product with the vector versions. So just to understand what the strain components mean, let's take a unit square and apply a displacement like this. That corresponds to a strain of only epsilon xx. The other strain components are 0. So we understand what epsilon xx is. Similarly, if we apply this displacement, then we get epsilon yy non-zero. All the other strain components are 0, so we understand what epsilon yy is. It's a stretch in the y direction. Now let's try to understand what gamma xy is. For this, we define a displacement like this, which causes the square to be deformed into a rhombus. And we realize that gamma xy is the total change in angle between the square and the rhombus. So we understand what the strain components mean geometrically. So everything we've talked about so far in terms of strain and stress does not depend on any particular material. Now the question arises, how is stress related to strain? This depends on the particular type of material, and the stress-strain relationship is called the constitutive equation, as we remember from our previous videos. In this video, we'll look, in fact, in this assignment, we'll look at isotropic linear elastic materials. So we'll see what this means. So isotropic means the properties of the material are same in all the directions. So if I cut out a piece of steel in any angle out of a sheet and put it in a tensile machine, I'll get the same answer, same measurements. So examples of isotropic materials are steel, concrete, sand. Examples of materials that are not isotropic, that means the properties are different in different directions. Some examples are wood and fiber composites. A material is called elastic if the stress-strain behavior is the same in loading and unloading. Examples of elastic materials are things like steel, rubber, up to a certain level of strain. Beyond a certain level of strain, we know, for example, that steel doesn't load and unload in the same way, but up to a certain strain level, these are elastic. Linear, we already know what linear is. We've talked about linearity of functions. So, for example, if I double the strain vector and that results in doubling the stress vector, that means the material is linear. So for isotropic linear elastic materials, it can be shown using symmetry arguments that there are only 2 independent material properties. Exactly what these 2 material properties, what 2 numbers are chosen as these 2 material properties is not unique. But for example, we can choose the Young's modulus and Poisson's ratio, which you must be familiar from undergraduate mechanics. So these properties can be determined from material tests, which you've probably done these kinds of tests also in undergraduate mechanics. So if you recall from undergraduate mechanics again, epsilon xx is related to sigma xx and sigma yy by this equation. 1 over e times sigma xx minus nu times sigma yy. Epsilon yy is 1 over e times minus nu sigma xx plus sigma yy. Gamma xy is 1 over the shear modulus, which you've probably seen. And the shear modulus is actually not a separate material parameter. It's related to the Young's modulus and the Poisson's ratio. And if you're interested, you can look up why. We can also write these equations in the other form with the stress vector on the left-hand side. And this matrix is called the constitutive matrix, which, as before, will denote by the symbol script E.